Okay, so here we would like to describe another type of Banach spaces. So we start with K being a compact metric space. So we know what a metric space is. Compact really means, in the simplest possible way, that every sequence has a convergent subsequence. Technically speaking, this is called sequential compactness, but it can be shown that sequential compactness is equivalent to the more technical notion of compactness that we're avoiding here for the moment being. So every sequence has a convergent subsequence. So the Bolzano-Warshaw's theorem is holds true here. Convergent, sorry about this. And this pretty much implies that every continuous function is bounded and has a minimum and a maximum. So every continuous function f from K to R is bounded and has a minimum, assumes, in other words, a minimum and a maximum. So obviously continuous functions on such a metric space form a vector space. And on this vector space, we consider the so-called uniform norm, which is the maximum of the absolute value of f of x for x in K. Okay, so it's not hard to show that this is a norm. Let's see. First of all, since it's a maximum of non-negative numbers, it's easy to see that it's greater than or equal to 0. It's also quite easy to show that it's 0 if and only if the function is the 0 function. The 3 lines here mean that the function is identically 0. And of course, again, it's quite easy to show that if we take the scalar multiple of a function, this is going to be the maximum of over k of lambda times f of x. And this, of course, the maximum over k of absolute value of lambda times absolute value of f of x. And here again, we can take two cases, lambda different from 0, in which case, as in the case of supremum, the lambda comes out of the expression of maximum. Actually, you can always argue that the maximum is a special case of supremum. And if lambda is 0, everything becomes 0. So in other words, we have this kind of situation. That means eventually lambda times the uniform norm of f. And how about the triangle inequality? We have two functions. Is it true that the norm of their sum is less than or equal to the sum of their norms? Well, that's actually quite straightforward to check, because if we take any element of x, then we have that this is less than or equal to f of x plus g of x. But then each of these is less than or equal to the norm of f plus the norm of g. So since this is true for any x, it will also be true for the maximum, which is obtained at some point. And this will be less than or equal to the sum of the two norms. And of course, this ends up being the norm of the sum. So we have established the triangle inequality. And what we would like to do now is show that this is a complete metric space, that this is a Banach space. And here we will try to outline the proof of a general theorem that says that the uniform limit of continuous functions is continuous. So, so start with a Cauchy sequence. Cauchy in C of k. And this means that the difference of the norms tends to zero as n and m tend to infinity. And if x in k is fixed, then of course this means that the sequence of real numbers fn of x is also Cauchy because it's dominated by the norm. So if we set f of x to be defined as fn of x, I'm sorry, the limit of fn of x, then this is a function defined on k. And obviously we have to show, as usual, two things. That, so to show, check that f belongs to C of k, and Fn tends to F in C of k. So we have to show both of these things. And as usual, it's easy to establish the uniform convergence without knowing a priori that it's continuous. But let's try to actually show both things. So first of all, what we have is given epsilon greater than 0, there exists n naught in n, such that if n is greater than n naught, then fn of x minus f of x is less than epsilon for x in k. Okay, so let's establish this. This is actually pretty straightforward. All we need to do is start with n naught in n, so that for n comma m greater than n naught, fn minus fm is less than epsilon over 2. Then this means that fn of x minus fm of x is less than epsilon over 2 for n comma m greater than n naught and x in k. So now if we fix x and we fix n, so for fixed n and fixed x, we pass to the limit as x tends to infinity. I'm sorry, as m tends to infinity, not x. Doesn't make any sense to say that. As m tends to infinity. And we get fn of x minus f of x is less than or equal to epsilon over 2 for n greater than n naught and x in k, which of course implies that fn of x minus f of x is less than epsilon over 2, is less than epsilon, sorry, for n greater than n naught and x in k. So if we show that it's continuous, then what we just, this relation that we showed implies that it tends, that fn tends to f. So if we establish continuity, for f, then the above relation will mean that fn minus f tends to 0. Okay, so we will be done. So all we need to do is show that we have continuity, and the only thing that we need in order to show continuity is this, because continuity has to be shown at any x naught. So to show that f is continuous on k, we need to show that it is continuous at every x naught in k. So fix x naught. So we fix x naught. And epsilon greater than 0. We need to find delta greater than 0, so that if d, and this is the first time that we allude to the metric of k, so this is the metric on k, d of x comma x naught is less than delta, then f of x minus f of x naught is less than epsilon. And here we do the classical epsilon over 3 argument. So we find two things. So first, we find let's call it k in n, so that fk of x minus f of x is less than epsilon over 3 for every x in k. Remember, that's exactly what this thing says. For any epsilon, we can find n naught, so that for n greater than n naught, we have this nice inequality. So we applied for epsilon over 3, and we don't even need to find all of them, or all the indices greater than n naught. We just need to isolate one of them. I'm sorry, so we don't need to reference all the indices. We just need to find one of them. So we find n naught plus 1. So k could be the first index for which that is true. So we get that. And now we know that fk is continuous. So since fk is continuous at x naught, there exists delta greater than 0, so that if the distance between x and x naught is less than delta, then fk of x minus fk at x naught is less than epsilon over 3. Okay, our claim is that this delta works for f. So this delta works for f of x, for x naught, and for epsilon as we want it. Indeed, f of x, so if the distance between x and x naught is less than delta, then f of x minus f of x naught, we want to relate these two things. We cannot relate them directly, but we can go through f sub k. So this is the same thing. And here it will become obvious why we needed epsilon over 3. So f of x minus f sub k of x plus f sub k of x minus f sub k at x naught plus f sub k at x naught. So we added and subtracted f sub k of x and f sub k of x naught minus f of x naught. And now by the triangle inequality, this is less than or equal to f of x minus f sub k of x plus f sub k of x minus f sub k at x naught plus f sub k at x naught minus f at x naught. So the idea is very simple. F sub k is really close to f. And so in some sense, their behavior is very similar. So if we have something that is we know in terms of proximity for f sub k translates to some type of proximity for the values of f. And of course, each of these things is less than epsilon over 3 for different reasons. Let's see why. So this and these two are less than epsilon over 3 because of the choice of k. And this middle one is less than epsilon over 3 because of the choice of delta that worked for the continuous function f sub k. So this means that it's less than epsilon, and we establish continuity at x naught. So this establishes continuity at x naught. And since x naught is any random point, i.e. f is continuous, since x naught is pretty much any random point. And now, as we said before, this relation right here tells us that f sub n minus f, now that we know continuity, tends to 0, and everything now is established. So so C of k is a Banach space. And of course, if you want to throw away all the generalities, the easiest one you can look at is C of 0, 1. So C of 0, 1 is a Banach space. And of course, it's just proven because 0, 1 satisfies the Bolzano-Weierstrass theorem, which tells us that 0, 1 is sequentially compact or compact according to the definition that we gave. This shows, by the way, that C of 0, 1, in C of 0, 1, functions have, in continuous functions in 0, 1, functions are bounded and have a minimum and a maximum. And that completes our account of C of k. Thanks for watching.